In the previous lecture, we studied two methods for solving linear systems. They are Gauss elimination and Gauss-Jordan elimination. We now have another method for solving a linear system, which is matrix factorization. In this system, in this method, we need to first write down the augmented matrix. AX equals B. AX equals B is the matrix form of the linear system. Here, A is the coefficients of the variables, and B is the right-hand side, or it is the constant terms. Here, we need to find L and U. L and U. You see, A is L times U. What's L and what's U? L is the lower triangular matrix, and U is the upper triangular matrix. Look, here, this is the matrix form of the system. If we have x1, x1, x3, x3 as variables, we say A, which is the coefficients of variables, is equal to L times U. L times U. This is L, and this is U. Okay? As you see, L is the lower triangular matrix, and U is an upper triangular matrix. Okay? It's only the above part of the main diagonal. It's U, and L is the lower part of the main diagonal. As you see, this is the diagonal here. This is the diagonal. Okay? It's the diagonal and above. This for U. And for L is the diagonal and below. But here, you should know what are the positions of the elements of these matrices. Look at matrix A. In matrix A, the first element here is A11, which is the first element in the first row. Okay? It's in the row 1 and column 1. That element. That's why we say A11. And for this element is in the second row and second column. That's why we write down A22. Then for this one, it's in the third row. It's the third row and first column. That's why the subscript is 31. It is 31. Here, L and U, you should know what are the position of L11, what's the position of L12, L22, L31, L32, and L33. And for U elements also. In U, we have these elements as well. We have these elements for U. Now, we say the matrix factorization is this. We say L times U is equal to A. Capital A is the matrix that you get from the coefficients of the variables. The multiplication of these two matrices is another matrix with the same size. With the size, look, if this is 3 by 3 and this is 3 by 3, these two must be equal. And the size of the outcome matrix is this. It's 3 by 3. Okay? So you get a matrix of 3 by 3. Here, the multiplication of these two matrices is this matrix. Do you know how to multiply two matrices? Let me tell you how to multiply two matrices. Okay? For these two matrices, what we do? We multiply the first row by all columns. Okay, then the second row by all columns and the last row by all columns. How? Let me write down here. If we have two matrices, let's say 3, 2, 1, 2, 0, 2, 0, 0, 5, multiplying by another matrix with the same size, 2, 2, 0, 3, 4, negative 1, negative 1, negative 2, 0. Okay, the multiplication of these two matrices is another matrix. Look, the multiplication of the first row with the first column, we get this element, A1. Okay, it is first row and first column, so you get A1. And first row with the second column, we get A1, 2. And then the first row by the third column, we get A1, 3. And then by multiplying the second row to the columns of the second matrix, we get the second row here. We get these elements. And then for others. Look, first we multiply the first row. First, we multiply the first row by these columns, by the columns of the second matrix. We always take the rows from the first matrix and columns from the second matrix. It's in the multiplication of two matrices. Here, the first row is 3, 2, and 1. Okay? We now multiply it by the first column. How? 3 times 2 plus 2 times 3 plus 1 times negative 1. That's how to multiply. The sum of these three multiplications, we get this element. Okay? What's the result? 3 times 2 is 6 plus 2 times 3 is 6 plus 1 times negative 1 is negative 1. And we get 11, is it? As 12 minus 1 is 11. So this element is 11. This is the outcome of the multiplication of the first row and first column. Okay? First row by first column. Then we multiply the first row by the second column. It's still the first row. We multiply the first row by all columns of the second matrix. Here, 3 times 2 is 6 plus 2 times 4 is 8 plus 1 times negative 2 is negative 2. And the result is 12. What's this? It is this element. Okay? It is A1, 2. Okay? Why? Because we get this in the multiplication of first row and second column. So it is 12. Then, for the other one, 3 times 0 is 0. 2 times negative 1, negative 2. 1 times 0 is 0. So the result is negative 2, is it? We get 0 minus 2 plus 0. It is minus 2. So this is minus 2. That's that element. Then we finished about first row. Then we take the elements of the second row. Okay? Now we write down as 2, 0, 2. Then we multiply this by all columns. Okay? Multiplying it by the first column, we get 2 times 2 plus 0 times 3 plus 2 times -1. 2 times 2 is 4. Plus 0 times 3 is 0. Plus 2 times -1 is -2. The result is 2. That's here, this element. This is 2. Then, for the second one, for the second column, 2 times 2 plus 0 times 4 plus 2 times -2. Okay? 2 times 2 is 4. 0 times 4 is 0. 2 times -2 is -4. And the result is 0. This element is 0. Now, for the third column, 2 times 0 is 0. Plus 0 times -1 is still 0. Plus 2 times 0 is 0. And we get 0. Okay? This is for that element. Then we multiplied the second row by all columns. What we do now, we take the third row. We finished everything with row 2. Then we take row 3. We take this row and write down here 0, 0, and 5. Then we multiply it by all columns. Okay, again we do it 0, 0, and -5. Then for the second column, 0, 0, -10. Then for the last one is 0. We get this matrix. This matrix is the multiplication of those two matrices. Okay? It's how to multiply two matrices. Now, in the multiplication of L with U, this is L and this is U. The multiplication of these two matrices is this matrix. Okay? Look, multiplying this row by this column, we get this element. Then multiplying this by this column, we get this element. Multiplying by this column, we get this element. Then multiply this row by all columns. Then this by all columns. As you see, we get this matrix. This is the multiplication of L times U. Okay? This is L times U. Look, U times L is different from L times U. Okay, in matrices, L times U doesn't equal to U times L. Be careful with that. You need to find L times U, L times U. Okay? Here, in matrix factorization, you can solve it in 2 steps or in 2 stages. First, we say Ly equals B. L is the lower matrix, lower triangular matrix, times Y. Y is a column vector of variables y1, y2, y3, and so on. Okay? Is equal to B. B is the matrix of constants, the constant terms, or the right-hand side constants. Then, after finding this, after finding y, we say u times x equals y. Here, y is y1, y2, y3. And x is x1, x2, x3. Here, we need to find the values of x1, x2, x3. Okay? To find these, what we do? First, we find L times Y equals B. Then, after finding Y from here we can get Y. After finding Y, we replace here and find X. U times X equals Y. Okay? That's the process. Ly equals B. In this case, we get the values of y1, y2, and y3. Okay? Here we use forward substitution to get the values of y1, y2, and y3. Look, the multiplication of these two, we multiply these two. It's the multiplication of this matrix with this matrix. We multiply first row by this. We get L11 Y1 equals B1. Here, B1 is noun, and L11 is also a constant noun. We can find Y1. Y1 is B1 over L11. And then for others, okay? I'm going to tell you how in solving the examples, okay? After finding y1, y2, y3, what we do, we multiply u by x, we equal to y. Here, in this case here, y are noun. Y1, y2, and y3 are noun. U is noun also, matrix U. So what's a noun? Only x1, x2, x3. It could be found easily. Okay? These are the values of x3, x2, and x1. Here we use back substitution. Look, what's the difference between forward substitution and back substitution? For forward substitution, we start from the first variable and then we substitute it in the others to find the values of other variables. Here, first we find y1, then y2, and then y3. This forward substitution. We substitute this here to get the second value. And then we substitute y1 and y2 here to get y3. But in back substitution, we start from the last variable. As you see, the last variable here is x3. We say x3 is this. Then we use x3 to get x2. And then we use x3 and x2 to get x1. That's back substitution. We return to find the value of other variables. Here we have two types of matrix factorizations, which are Doolittle and Court factorizations. We have these two methods. First, we have Doolittle factorization. Okay? What's Doolittle factorization? In Doolittle factorization, we just replace the main diagonal of L by 1. Look, L, U. U is still the same, but L, the main diagonal elements become 1. This is Doolittle factorization, okay? If it's mentioned, use Doolittle factorization, you should use these L and U. U is still the same as above. It is apportioning the matrix from main diagonal to up. Okay? But L becomes, look, the lower of the main diagonal are L's. Okay? But the main diagonal elements here are all 1s. Okay? This is Doolittle factorization. We do the same procedure as we did before to get the values of x1, x2, and x3. Here, this is L, this is U. Multiplication of these two is this matrix. Then we find the values of L1, L21, Ln1, L up to n. Okay? We find these values of L's and U's. Look at this example. In this example, it says, find the LU factorization of the matrix using Doolittle form. First, you need to find L and U. Okay? L and U. Then, it says, use it to solve the linear system. Use it to solve the linear system. This matrix is matrix A. So you say L is as you see, this is a 3 by 3 matrix. That means both L and U must be 3 by 3 matrix. L is 1, 1, 1. The above elements are all 0. Okay? Because it's lower triangular matrix. Then, what's this element? It's L 2, 1. Is it? At second row, first column. It's L 2, 1. How about this element? L 3, 1. And this element is 3, 2. This is matrix L. And what's matrix U? It is U11. Is it? U12. So it's U22. And U33. Okay? The below elements are all 0. How about the above ones? The above ones are not, because it's upper triangular matrix. Okay? So it's U 1, 2, U 1, 3, U 2, 3. These are the elements of U. And the above one is L. And this is U. Okay? These are matrices L and U. Now, we need to multiply these two and equal it to what? To matrix A. This is matrix A. This is matrix A. Okay? So you should know how to find matrix A from the linear system. It's the coefficients of x1, x1, x3. Okay? Now, we say LU is equal to A. Okay? We now multiply matrices L and U, okay, and we equal it to this matrix. Okay, now let's find the multiplication of these two matrices. By from multiplying this row by all columns here, what we get? We get, so this equals to, let me write down the multiplication here. Look, multiplying this row by these columns, 1, 0, 0. 1 times U11, 0 times 0, 0 times 0. We get U11, is it? Then, multiplying by this column, we get U12, look, 1 times U12, 0 times U22, plus 0 times 0, and we get U12. Then, multiplying it by the third column, 1 times U13 is U13. Okay? Then, 0 times U23, it is 0. 0 times U23, 0. Okay, so the result is this. Now, we say this matrix is equal to this matrix. If these two matrices are equal, so this element must equal to this one. Okay, and this element must equal to this one. So this element must equal to this one. Okay, the elements with the same position must be equal. So what's U11? It is 1. What's U12? It's 2. What's U13? It's 1. So these are the values of U11, U12, and U13. Now, we replace these by their values that we found in the first step. In the first step, we just multiply the first row by first columns, by columns of the second matrix. Okay? In the first step, in Doolittle factorization, what we do, we multiply the first row of L by all columns of U. And then we get the values of U11, U12, U13, as we found. Okay? That's it. We now replace these by the values as we found in the first step. Okay? Then what we do, we multiply the second row. Look, this process is always the same. Okay? In the first step, we just multiply the first row by all columns, and we get the elements of U11, U12, U13. Okay? We get the values of U12, U13, U11, U11, U12, U13. Okay? And also, you can just say that it is here U11 is this element, U12 is this, and U13 is this. It's true for only U11, U12, U13. It's not true for others to say it's the same position. Okay? You can just say it is U11 is this value, this value. U12 has this value and U13 has this value. Okay? You can just say that. It's in the first step. After finding these three, we replace U11, U12, U13 by their values in the matrix of U. Here we replace this by 1, this by 2, this by 1. And let's see what we get. We get this matrices. We get these matrices. Okay? Now, we say L21, L31 are the same as these two variables, these two values. They have the same as this, but sorry, it's not the same actually. Here we say we multiply this. Look, in the first row, everything is noun, and here in the first row, everything is noun. In the second row here, if you multiply it by the first row here, what we get? We get 1 times L12. Look, if you multiply this row by this column, let's see what we get. We get L21, 1 and 0. Multiplying these two plus, multiplying these two plus, multiplying these two. Okay? What we get? We get L21 plus 0 plus 0. So you get L21. L21 is equal to what? Equal to this. Look, this is A21. Is it? It's A21. Let me write down the multiplication. We already found these three variables, which are 1, 2, 1. These are the multiplications. Okay? Then, in multiplying this by the first column, we get L21. Okay? Then, multiplying this by the first column, we get L31. So it's 3, 1. Okay? This is the multiplication of these two. This is the multiplication of these two. It's here we get these, and the multiplying this and this by the first column. In the first step, we say U11, U12, U13 are these values. In the second step, what we say, we multiply the second row and the third row of matrix L by the first column of matrix U. And you get these two elements. So these two elements are the same as these positions. This is 1 and this is 3. Is it? That's 1 and that's 3. Now this is 3 and this is 1. We found these two. So we replace these two by their values. This is 3, this is 1. And we get these two matrices. Now, what else should you find? It's easy to find these two. Okay? How? By multiplying the second row. We don't need to multiply by this one because everything is known here. But here and here, we have some unknown variables, which are U22 and U23. We multiply the second row. It's in the third step. In the first step, we said U11, U12, U13 are those values. In the second step, we multiply second and third rows of matrix L by the first column of matrix U. And we get the values of L21 and L31. Then, in the first step, we multiply only the second row by second column and by third column. Okay? We multiply the second row in matrix L by second and third columns of matrix U. Let's see what we get. If we multiply 3, 1, and 0, it's 3, 1, and 0. By the second row, as 3 times 2 is 6, plus 1 times U22 is U22. 0 times 0 is 0, we don't. Okay? What we get in this multiplication? What we get? In the matrix of multiplying these two, which element do we get? We found this. Now, as we have the multiplication of row 2 and column 2, so which position do you get? 2, 2. So you get this position. This is 6 plus U22. Is it? This equals to what? Equal to this position. Okay? If this equals to 1, so U22 is -5. U22 is -5. If we move this to the other side, you get -6, and you already have 1, so you get -5. This is -5. What's -5? U22. Then multiplying the second row by third column, 3 times 1, plus 1 times U23, plus 0 times U33. What we get is 3. This is U23. The sum of these two, this is 0. It's 3 plus U23. What's this position? Here we get this from the multiplying second row by third column. It's U. We get this here, which is 3 plus U23. This equals to what? Equals to this position. This equals to 1. And so U23 is -2. So now we get U22 is -5 and U23 is -2. Now we replace these two by their values. And we get this. These are the values of U22 and U23. So what are unknown here? L32 and U33. L32 and U33. You can multiply this by this column. Okay? You can multiply this by this column. What we get? We get 1 times 2 plus L32 times -5 plus 1 times 0. Okay? What we get? 1 times 2 is still 2. Minus L32 times -5. Minus 5 L32. Plus 1 times 0 is 0. This equals to what? Here, we get this in multiplying third row by second column. Third row by second column, you get this position here. This equals to what? To 4. So this equals to 4. And we get 5L32 equals -2. So L32 is -2/5. This is L32. We found L32 also. We now replace this by -2/5. That's it. Then for this one, we multiply this by that, and we equal it to 2. Okay? We get the result will be 1/5. We multiply the third row by third column. 1 times 1 is 1 plus -2/5 times -2 is plus 4/5. Then 1 times U33, this equals to what? To 2. Because here we multiply third by third, so it is this position. It equals to 2. Now we move this to here, we get, and this also to there. We move these two to the right hand side. We get U33 is equal to 2 minus 1 minus 4/5. 2 minus 1 is 1. We get 1 minus 4/5. This equals to 1/5. U33 is 1/5. Here we find common denominator, which is 5. We get 5 minus 4/5, which is 1/5. This is U3. So U33 is 1/5. Up to now, we just found U and L, nothing else. Okay? We just found the values of matrices U and L. Now we say Ly equals B. It's given, B is given. L is this matrix. Okay? We just multiply L by Y and equal it to B to get the values of Y. Y is what? It's Y1, Y2, and Y3 here. After finding these, what we say? We say U times X equals Y. Y is this column vector, and X is X1, X2, and X3. We multiply U by X equal to Y to get the values of X. X1, X2, and X3. X1, X2, X3 are the solutions of the system. They are the solutions of the system. So here we need to find X1, X2, and X3. Up to here, we found U and L. We just found U and L. After finding U and L, what we do? We say Ly equals B, it's for the first step, and then Ux equals Y as the second step to get the values of X1, X2, and X3. Look, this is U, this is L, sorry. L times Y equals B. B is given at the beginning. That's it. This is B. B is the matrix of constant terms. Okay? We say Ly equals B. L times Y equals B. Look, look at this multiplication. We multiply this by this. We equal it to this, to the first element, sorry. And also, you can say 1 times Y1 is 8. So Y1 is 8, is it? It's 8. Let's do the multiplication. It's easy to find. Multiplying these two, this by this, what we get? 1 times Y1 plus 0 times Y2 plus 0 times Y3. So you get only Y1. Is it? Y1 equals the first element here, equals 8. Then the second row by this, what we get? We get 3 times Y1 plus 1 times Y2. So 3Y1 plus Y2. 1 times Y2 is Y2. 0 times Y3. 0. It equals to what? The second element here, which is 11. Then the third row by the third column. Sorry, by this column. 1 times Y1, which is Y1. Minus 2 over 5 times Y2. Minus 2 over 5 Y2. Then 1 times Y3. This equals to what? 14. Now, this is for substitution to get the values of Y1, Y2, and Y3. Y1 is 8. Okay? In the second equation, we have Y1 and Y2, but we need to substitute the value of Y1. Y1 is 8. In the first equation, we get that Y1 is 8. So we replace this by 8. So it's 3 times 8. And we get 3 times 8 is 24. Plus Y2 is 11. What's Y2? Minus 13. It's Y2. And this is Y1. In the third equation, we have Y1, Y2, and Y3. We need to find the value of Y3. But we already found the values of Y1 and Y2. We just replace them by their values. Okay? We replace Y1 by 8 and Y2 by negative 13. What we get? Y1 is 8 minus 2 over 5. Y2 is minus 13 plus Y3 is 14. We multiply negative 13 by minus 2 over 5. We get 8 plus 26 over 5 plus Y3 equals 14. From this, you can get the value of Y3, and Y3 is 4 over 5. We just move these two to the other side and get the result. Y3 is 4 over 5. That's it. Okay?
If you don't have a calculator,
okay,
we can't find it by the space. We can't find it in the point, like the board.
Here, in the exams, you don't have to write down in decimal places. Okay? You should write down as fractions. Okay? So calculator gives you the decimal places. It doesn't give you this. Okay? If you use calculator, you cannot get this by using calculator. It will give you decimal places like this. 5 is 0.4. Sorry, not 0.4, 0.8. You don't need to write down in this form. You should write down in this form. Okay? And it's easy to get this. It's easy. Here, you just need to move these to the other side. Only leave Y3 in the left and move others to the right. Then calculate it. find the common denominator, you get the result, which is 4 over 5. That's it. Now, these are y1, y2, and y3. What's y? Y is the transpose of this matrix. Or y is 8 minus 13, 4 over 5. This is y. That's how to find y. By multiplying L by y equals b, we get the values of y1, y2, and y3. Then we use y to get the value of x. x1, x1, x3. What we say? We say ux, u is a matrix that you found before. This is u, and this is L. We already found this. Okay? This is u, and this is L. We found before. We say u times x equals y. What's x? X is x1, x2, and x3. Okay? What's y? Y is this matrix. We do the same as we did in the previous step. But here, we start from the last one to the first one. Look, this is u, this is x, equals y. This is x, this is y, and this is u. Okay? We start from the last to the first. Multiplying this row by x1, x2, x3, what we get? We get 0 times x1 plus 0 times x2 plus 1 over 5 times x3. We get 1 over 5 x3 is equal to what? Equal to the last element here. That is 4 over 5. So x3 multiplying both sides by 5, we get 4. This is x3. x3 is 4. Then, look, we found that x3 is 4. Then we multiply the second row by x1, x2, x3. This element is multiplied by x1, which is 0. 0 times x1 is 0. Then negative 5 times x2, which is minus 5 x2. Okay? Then minus 2 times x3, which is minus 2 x3 is equal to what? Equal to the second element. As we multiply the second row by x, we equal to the second element in the right hand side, which is minus 13. Here, x2 and x3 are unknown. But we already found x3. It is 4. It is 4. We will just replace x3 by 4. We get 2 times 4. What's 2 times 4 is? 8. It's minus 8. Now, we move this to the other side. If we move it to there, we get minus 5x2 is equal to minus 13 plus 8. What's minus 13 plus 8 is minus 5. That means minus 5x2 is minus 5. Minus 5x2 is minus 5. To get x2, we need to divide both sides by negative 5. What we get? x2 is minus 5 over minus 5, which is 1. That means x2 is 1. x2 is 1. Okay? Then, for finding x3, so x1, you found x2 and x3. For x1, what we do, we multiply this by this column and equal it to this. We get 1 times x1 which is x1, plus 2 times x2, plus 1 times x3 is equal to 8. We already found x3 is 4, x2 is 1. So you replace this by 4 and this by 1. What we get? x1 plus, if you replace this by 1, this is 1, x2 is 1, and x3 is 4. 2 times 1 is 2, plus 4 equal to 8. This is 6. Moving to the other side becomes minus 6. 8 minus 6 is 2. So x1 is 2. That's it. It's the value. Look, in these two steps that I use in the last two steps, what could you do? Look, you could use these three equations for finding y1, y2, and y3. This is L times y equals b. Okay, L times y equals b. You can say y1 is this, y2 is this, y3 is this, directly. Okay, and in the multiplying u by x, which equals to y, it's the last step. It's x3 is this, x2 is this, and x1 is this. But here, after finding x3, you need to replace here to get x2. After finding x2, you need to replace x1, x3 here to get x1. That's all. Okay? You can memorize these three equations and these three equations. But here, this is for Ly equals b. This is for ux equals y. Y, you should first find y and then use this step. Okay, that's all. So here, it's important to find matrices L and U. After finding these two matrices, you say Ly equals b to get the values of y1, y2, and y3. And then ux equals y to get the values of x1, x2, and x3. It's in Doolittle factorization. We now have Claude factorization. Okay, we have another factorization. It's the same, but instead of replacing these by 1, what we do? We just replace these by 1. Okay, it's Claude factorization. In Claude factorization, it's the same procedure. It's the same procedure. And instead of replacing these by 1, it's in Doolittle factorization, we replace these by 1. But here, in Claude factorization, you will replace these by 1. Okay? We replace these by 1. We do the same. L times U equals A. We do the same procedure. Okay? We do the same. This is the matrix. This is the matrix form of the system. This is A and this is B. We say LU equals A. In Claude factorization, it says use Claude form. So here, L, in the diagonal, we have L11, L22, L33. But in U, we have ones for diagonal elements. This is L, and that's U. We need to find these elements. Okay? We need to find these elements. We say L times U equals A. That's it. Now we do these multiplications to get the values of L11, L12, and all L's and U's. Okay? That's it. These are L11, L21, L3. By multiplying these three, by the first column here, we get the values of L11, L21, L31. It's the same procedure. That's why I'm not gonna do it again. Here, we multiply this by the second column and third column to get the values of U12, U13. Okay. Then for other values, that's all. Now, this is U, this L, and that's U. Okay, this is L, and that's U. It's the same procedure as before, as the previous example. That's why I'm not gonna do it all. Okay, it's the same, multiplying to get the values of U's and L's. Then we say Ly equals B. B is given. Okay, this is L, matrix L that you found. This is Y. Y is Y1, Y2, Y3. We see Y1 is minus 12 dividing by this. Okay, Y2 here. What's Y1? Let me show you again. That's it. This is Y1. It's B1 over L11. We already found L11. Okay, and B1 is given. We can get Y1. And Y2 is B2 is given. L21, we found it. L22, we found it. And Y1, we found it in the previous step. Okay, so we get Y2 and Y3. After finding these three, we use these three in U times X equals Y to get the values of X1, X2, X3. We use these three values, so Y3, Y2, Y1, to get the values of X3, X2, and X1. That's it. Ly equals B, Y1, Y2, and Y3 could be obtained from this. After finding Y1, Y2, Y3, we say L is a U times X equals Y. These are the values of Y1, Y2, and Y3. We get the values of X3, X2, and X1 by the formula in the above that I showed you. Okay? And these are the values of X3, X2, and X1. So this is the solution of the system. But here, if it's asking about finding U and L only, you just do up to here. You don't need to find the values of X1, X2, X3. But if it says solve the system, you need to find the values of X1, X2, and X3. Okay? You need to find the values of X1, X2, and X3. And so it's the end of this chapter. If you have no questions, we'll take a break for 5 minutes, then we will be continuing to the new chapter. Okay? Do you have questions? So let's take a break for 5 minutes. Chapter 2, it's about Euclidean vector space. Here, we just talk about some operations on vectors that will be based for the next chapter. Okay? Here, we talk about only some basic operations on vectors. First, you should know what's a vector. A vector is an n by 1 matrix, okay, with n entries. Here, we say the vector, let's say V is a vector like V1, V2, up to Vn. Here, V is a vector. It's represented in this way, or V is V1, V2, up to Vn. Okay, it could be represented in this form, or also here we have these two forms to represent a vector. Okay, these are vectors. It's nothing here. Vectors in Rn. We say if we have n tuples, for example, here for u1, u2, u3 up to un, how many elements do you have here? How many entries? N. So it's n tuples. Okay? It's n tuples. This is in Rn. It depends on how many elements or entries do you have in the vector. If we have, let's say, two, let's say v1 and v2. How many entries do you have? Two. So it's in R2. Okay? If we have three elements, let's say v1, v2, v3. It's in R3. And if you have four elements, we say it's in R4. As you said, we could represent this in the other way, which is v1, v2. And this one as a column vector, we could represent by v1, v2, v3. Okay? For R2, we have only two elements. We have an order pair. V is 1, 2, 1 and 2. Here, the entries here, u1, u2, u3 up to un, these are real numbers. They could be positive, they could be negative values, they could be fractions, they could be zero, okay? They could be any real number. So this is a row vector, and this is a column vector, okay? If it's a horizontal vector, we say it's a row vector. But if it's a vertical vector, it is a column vector. Okay? These are in R2, belongs to R2. Okay? You have only two elements in there. You have only a pair. In R3, we have this row vector, and this is the column vector of the same vector. Okay? It could be written either in a row, or in a column. This is called a column vector, and the above one is a row vector. It's for R3. These are in R3, as we have three elements in the vector. These are for R2, these are R3, these are for R4. Okay? As I said, the elements of the vector could be any real number. As you see here, we have a fraction. Here we have negative, we have zero, we have irrational value, pi. Okay? It's an irrational value. We always use boldface lowercase letter for representing a vector. We use V, it's a little v, boldface. Or U is a boldface, it's a little u. Any other letter, okay? A, B, or any other little boldface letter, okay? That's it. We either can represent by a lowercase boldface, or if the initial and the terminal points are given as this vector. This is A and this is B. Okay? It's given. Initial and terminal points. The initial here is A and the terminal is B. It starts from A to B. You could represent this vector by A, B. Okay? You could represent it by either this way or V, a little v, boldface. Okay? That's it. If the initial and terminal points are given, you can represent the vector as this way or by a little bold-faced letter. And when we talk about vectors, we need to think about magnitude, directions, and lengths. Okay? Length and magnitude are the same. Magnitude is the length of the vector. Magnitude is the length of the vector. We say if two vectors have the same magnitude, that means they both have the same length, like this. These two vectors have the same length. This length is equal to this length. But if they are in different directions, we say those two vectors are not equivalent. They are not equal. Okay? We say they are different vectors because they have different directions. This one is in this direction and that one is in that direction. Even they both have the same magnitude or the same length, but they have different directions. So those two vectors are not equal. Those two vectors are different and are not equal. Even if we have two vectors with the same direction, as you see, the direction of this one is here. And this is the direction. And the direction of this one is this. Both have the same direction. How about their magnitude? Which one has more length than the other one? This one. Okay? So these two vectors have not the same length or their magnitude are different. That means these two vectors are different or those two vectors are not equal. In two cases, we say two vectors are not equal if they have different directions or if they have different magnitude or length. In these two cases, we say the vectors are not equal. But if two or more vectors have the same direction and the same magnitude, as you see, this and this length is equal to this length, and both have the same direction, we say those two vectors are equal. And even this one and this one, this length is the same as those, and this also. So these vectors are equal. We say if two vectors are equal, we say those two vectors are equivalent. The vectors are equivalent. So here we have equivalence vectors. We have these four vectors which are equal. We say these are equivalence vectors. The same magnitude and the same direction. Okay? Even if their initial and terminal points are not the same. Look, the initial and terminal points of this vector are here. And this one are here. This one are here. This one are here. Even the initial and terminal points are not equal, but if the vectors have the same length and the same direction, we say those two vectors are equivalent. Okay? To replace a vector for R2 and R3, we always start from the origin. We always start from the origin to the point which represents the vector. For example, here, if we have a vector to be 2, 3, Okay, this is a vector. 2 and 3 is a vector. What's the x value in the vector? 2, is it? And the y value is 3. First, what's 2 and 3? 2 on x-axis and 3 on y-axis. 2 on x and 3 on y. That's it. Is it? This is 2 and 3. To represent the vector geometrically, we start from the origin to that point. Okay? We start from 0, 0 to this point. This is the geometrical representation of this vector. This is the geometrical representation of this vector. This is x value. This is x value. And this is y value. Okay? So this is the red one is the geometrical representation of this vector. And the red one, the length of the red one is the magnitude of the vector. The length of this one is the magnitude of the vector. Okay? Look at this. Here we have this vector. To represent this, so 1, 2, 1, 2. Here we have x is 1, y is 2. Let's represent this point. 1 and 2. That's it. Okay? How to represent this vector? Look. Represent x is 1. Okay? And y is 2. Then the vector starts from the origin to the terminal point. That's it. The red one is the vector, is the representation of the vector. Okay? And the length of the red one is the magnitude. This point is 1 and 2, which is the terminal point. That's it. We say a zero vector is a vector with all elements are 0. A zero vector is a vector with all elements 0. The negative of a vector is a vector in which has the same magnitude or length, but in the opposite direction. In the opposite direction. For example, here we have v, which is this vector. So negative v has the same length, but in the opposite direction. It's exactly opposite to this vector. So it is here, but it must have the same length. Okay, let's see. If we have this vector, let's say it's u. So negative u is exactly opposite to u. This is minus u. With the same length, it must have the same length, but in the opposite direction. Okay? What if we have this? Let's say this is u. Oh, let's say it's u. If this is u, how about negative u? It is in the opposite direction with the same length. This is u, this is minus u. Okay? It's how to find the negative of vector. If v to be a vector, when you say minus v, you need to give a negative value to all of the elements. to all of the components of the vector. We now have adding two vectors. For adding two vectors, if u to be this vector and v to be this vector, if u to be this vector and v to be this vector, so u plus v is, look, it's adding these two vectors. How? These two components together, a plus c and b plus d. Okay? In adding two vectors, the vectors must have the same number of components. Okay? So here we have two elements in U, so you must have the same number of elements in V. You cannot add U and V if in U we have 3 elements and in V we have 2. So they must have the same number of elements. And then we just add these elements together, the same position, okay? A with C and B with D. Even if we have more and more elements, we do the same. So U and V is A plus C and B plus D. In adding two vectors, we get a vector. We get a vector with the same number of elements. A plus C is an element. B plus D is another element. So U plus V is A plus C and B plus D. If this is V and this is U, so U plus V is this vector. Okay? In adding two vectors, we get either these shapes. If U to be in this direction and V to be in this direction, then adding U and V is in this direction. It is in this direction. Okay? If W in this direction and V to be in this direction, then W plus V is in this direction. If W to be in this direction and V to be in this direction, so V plus W is here. It is here. If you have numbers, it's easier, so you don't need to memorize these figures, okay? You don't need to memorize these. If V and W to be values, it's easy to get these shapes. Just replacing the vectors, you'll get those shapes. We now have, if we have a scalar multiplication of a vector, okay, if the scalar is positive, we have only change in the length or magnitude. For example, if this is U, if this is U from here to here, this is U. So 3 times U is in the same direction, but it's 3 times of U. The length becomes 3 times of U. Okay, so 3 times U is this. This is 3U. Here, it's in the case if the scalar, this is the scalar, is positive. Only the length is going to be more or less. So if we have a half of U, how about this one? A half of U, look, the scalar is positive. It's a half. Okay, but the length becomes a half. This is half of u. Okay, that's it. But if the scalar is negative, if it is negative, it is in the opposite direction, and the length is going to be changed also. Okay, here you have an example. This is v, this is v. To get minus 2v, so first you need to find minus v. What's minus v? It's the same in the opposite direction. Okay, it's minus v. What's 2 times this? So the length of the green one becomes double because it's multiplied by 2. Is it? So you get this. This is minus 2v. If the scalar is negative, so you get a positive direction. So I mean opposite direction, and also the length is going to be changed, depends on the scalar. How about 3v? 3v is the same direction as v, but the length is triple of this. Okay? A half of v, as the scalar is positive, has the same direction, but the length becomes a half. Okay? The length becomes a half, or the magnitude is a half. Here we see the sum of two vectors. I mean the geometrical representation of sum of two vectors is a parallelogram. Here, this is u, this is v, and this is u. U plus v is this vector. If we just join these three peaks, we get a parallelogram. Okay? We get a parallelogram. So the sum of u and v is a parallelogram. Here, for adding two vectors, if we have u and v, adding them, we just add these two, and so on for the end. Okay? We just add their respective elements. Look, u plus v is u1 plus v1 plus, and then comma, u2 plus v2 up to un plus vn. That's all. As I said, the sum of two vectors, the geometrical representation of sum of two vectors is a parallelogram. So the difference of two vectors is the same. The difference of two vectors is the same. This is minus w, and this is v. So v minus w is this. If we just join these three peaks, we get this parallelogram. That's all. Okay? V minus w is the same as to say v plus minus w. So we represent v and minus w. Then we find v plus v minus w. V minus w is this vector. That's it. We represent it. Then we just join these three peaks. We get that parallelogram. If we multiply a vector by a scalar, so we multiply all the elements by the scalar. Okay? We just multiply all the components of the vector by the scalar. Here, if we multiply k times u, we multiply all the components here by k. Here we have these vectors, u and v. It says, what's u plus v? We just add respective components. 1 plus 8 is 9. 4 plus 1 is 5. Then 5 plus minus 2, or 5 minus 2 is 3. 3 minus 1. So minus 3 minus 1 is minus 4. That's it. It is the sum of those two vectors. Then 2 times u. We just multiply these elements by 2. We just multiply these elements by 2. Okay, because here we have 2u. Then 2u minus 3v. We first multiply elements of u by 2, then elements of v by negative 3, then we add them. Okay? Look, this is 2 times u. If we multiply u by 2, what do we get? We get 2 times 1, 2 times 4, 2 times 5, 2 times negative 3. We get this vector. Then plus minus 3 multiplying by v. We just multiply this by negative 3. Negative 3 times 8, negative 3 times 1, times negative 2, times negative 1. We get this vector. Now we add these two. 2 and negative 24 is negative 22. 8 plus negative 3 is 5. 10 plus 6 is 16. Minus 6 plus 3 is minus 3. So this is 2u minus 3v. That's it. This is 2u minus 3v. It's just to know how to multiply the vectors by a scalar and how to add and subtract vectors.
If we draw in the picture.
It's in R3. It's in R3, so it's not include field.
I know.
Okay.
Give us 40.
Here you cannot draw this. You cannot. Here we have we can draw in up to R3. No, not R4. Okay, we cannot draw it. Okay, we just can draw up to R3. This X, Y, Z. You cannot draw pictures in R4. Okay. Here we have these properties of vectors. We say it's associative with addition. If you have 3 vectors, you can add any of those 2 vectors first. Okay? Here, you can add uv, then adding to w, or vw, then adding to u. It's up to you. Both are true. If you add a 0 vector to any vector, it's still the vector. Here we have the inverse addition. U plus negative u is a 0 vector. If we subtract a vector from itself, we get a 0 vector. Here, addition is commutative. We can say u plus v is equal to v plus u. And if we multiply a scalar by the sum of 2 vectors, we can multiply it by both vectors. It could be multiplied by both vectors. As you see, it's k1u, k1v. Then, if we have the sum of 2 scalars which is multiplied by the vector, we can multiply the vector by both scalars. If we have the multiplication of 2 scalars by a vector, you can just multiply 1 by 1 to the vector. And if we multiply any vector by 1, is the vector itself. So it's enough for now. Okay. We now have norm and distance of a vector. For finding norm and distance of vector, what we do? For finding the norm or length or magnitude, these all are the same. Okay? Norm is denoted by for vector v, if we have vector v, its norm is denoted by in these lines. Okay, it's denoted. It's the norm of vector v. We say if you have two components in the vector, and we have only two components of the vector, let's say v is v1, v2. Then norm v is the square root of v1 squared plus v2 squared. That's all. But if you have three components in R3, we say it's v1 squared plus v2 squared plus v3 squared. It's the sum of squares of all components. Okay? It's the length, norm, or magnitude of a vector. This is norm, length, or magnitude. Magnitude of vector. Okay? If it's asking for finding the norm, the length, or magnitude of a vector, we use this rule. It depends on how many components do you have in the vector. It's the square of all, the sum of squares of all components. Okay, that's it. If you have n elements, or we have n tuples, a vector with n tuples, if we have n components in the vector, then its norm here, the norm of, let's say, u, is the square root of u1 squared plus u2 squared plus up to un squared. Okay, un squared, even for v. Now, to find the distance of two vectors, in two vectors, for two vectors, we have distance. Okay, the distance of two vectors u and v, we say it is d, it's denoted by d of uv. This is the distance of u and v. It's also known by Euclidean distance. It's Euclidean distance, okay, or distance. Distance or Euclidean distance are the same, okay? For finding the Euclidean distance of u and v, it is the square root of, as this is u and v, it depends on you. Which one do you subtract from the other one? Okay, in both cases, it's true. I'm saying u1 minus v1 squared plus u2 minus v2 squared plus up to un minus vn squared. As we have n components in each, so the distance of u and v f is u1 minus v1 squared plus u2 minus v2 squared up to un minus vn squared. And also, you can see it is v1 minus u1 squared. It's the same. In both cases, you get the same result. Plus v2 minus u2 squared plus up to vn minus un squared. In both cases, you get the same results. Okay? For finding the norm or length of a vector, if we have n components in the vectors, that's it. It is how to find the length, magnitude, or norm of a vector. And the distance of u and v is the norm of u minus v. It's the same. What's the norm of u minus v? It is u1 minus v1 squared plus u2 minus v2 squared plus up to un minus vn squared. Okay, let me write down there, plus un minus vn squared. Okay, this is the same rule as we took for this, for the distance of two vectors. It's the norm of u minus v. Here we have given the vectors u and v. It says find. Let's find the norm of u. What's the norm of u? Or length of u? Or magnitude of u? It is the square root of the sum of squares, all components of u. What are the components of u? 1, -2, 4, 1. So it's 1 squared plus -2 squared plus 4 squared plus 1 squared. That's all. Okay? That's all. And this equals to the square root of 1 squared is 1. And -2 squared is 4. 4 squared is 16. 1 squared is 1. The sum of these is square root of 22, is it? So this is the length of u. How about the length of v? What's the length of v? Is equal to what? We just squared these all in a square root. 3 squared plus 1 squared plus -5 squared plus 0 squared. This equals to what? This is 9, this is 1, this is 25, this is 0. What's the result? It is the square root of 35. These are the length or norm or magnitudes of u and v. No, it's square. It's even. The exponent is even. اگر توانك جود بو مجرد. Okay? That's it. Now, to find the distance of u and v. To find the distance of u and v. The distance d of u and v is what? As the square root of u minus v, u minus v, u minus v, u minus v. Okay? What's the first one? 1 minus 3 squared. Okay? It's u1 minus v1 squared plus u2 minus v2 squared. So it's -2 minus 1 squared. Okay? Then u3 minus v3 squared. 4 minus -5 squared. Then plus 1 minus 0 squared. Now we simplify it first. This equals to the square root of 1 minus 3 is 2 squared. Minus 2 minus 1 is -3 squared. Now, 4 minus -5 is +5. 4 plus 5 is 9. Then 1 minus 0 is 1 squared. It is the square root of 2 squared is 4. 3 minus 3 squared is 9. Since the exponent is even, so it becomes positive. We get 9. 9 squared is 81. 1 squared is 1. It is square root of 96. This is the length of u and sorry, the distance of u and v. This is the distance of u and sorry. It is 20. It's 95, not 96. It's the square root of 95. This is the distance of u and v. And here is the length of v, or the norm of v. We already found this. Okay? It's how to find the distance of two vectors. and also how to find the length of a vector. That's all. We now have this vector, these two vectors actually. It says find the Euclidean distance between U and V. That's easy. The distance of U and V is U minus V, U minus V, U minus V, U minus V. All squared, we get the square root of 218. We just solved an example like this. Okay, it's similar to the above one. That's all. That's the same. Okay, it's the same procedure actually. Okay, the distance of two vectors could be obtained by this one's the norm of U minus V, as we did before. Then we have two products, dot product and cross product of two vectors. We have dot product and cross product of two vectors. If the angle between the vectors is given, we use this rule for finding the dot product of the vectors. Dot product of U and V, here we get a scalar. Okay? For cross product, U cross V, we get a vector. Here it's a scalar. This is a vector. In cross product of two vectors, we get another vector. But in dot product of two vectors, we get only one value. We get a scalar. Okay? If the angle between the vectors is given, we use this rule for finding the dot product of two vectors. Okay? That's it. Here you have some examples. So let me check if you could finish this or not. Okay, let's finish here. That's enough for today because you have a quiz.